Welcome back to Bio 6612. And today I'm going to cover the likelihood derivation for conditional logistic regression. And this can get pretty complicated. I'm not going to expect you to be able to drive this on homework or on a test, but it is something that's good to see and have exposure to. So from last lecture, modeling data from matched studies, we can use a logistic model where pk of xi of k represents the probability that the ith person in the kth matched set has disease, where k indicates the strata or the current matched set, I indicates an individual in the current matched set where you have m plus 1 individuals, where m is the number of controls. I'm assuming one case here. And I equals 0 indicates the case for that case, the person who's the case for that set. And this bold xik is a vector of covariates for the ith person in the kth matched set. So we can construct a likelihood function that allows us to find estimates for the parameters of interest beta by first finding the conditional likelihood for the kth stratum or matched set. I'm going to use the word stratum and matched set interchangeably here. And then in the second step, you combine these likelihoods across strata to obtain a single likelihood function. So for the conditional likelihood, we need the probability that the individual in the study whose vector of covariates x0k is actually the case, conditional on the observed covariate values for all of the other individuals in the kth matched set. And so here we defined pxik of y equals 1 to be the probability that a person with disease in the kth matched set has covariate vectors xik, values xik, and the probability xik given y equals 0 to be the probability that a person without disease in the kth matched set has that same covariate vector. Then you can calculate the joint probability that x0k corresponds to the case, and everyone that this person, this set of covariates corresponds to the case, and all of the other covariate vectors are the controls. And this actually should be 1 to m, not 0 to m. Then this joint probability is given by the product of the probability for the control times the probabilities for each of the cases. And the reason that we can get this joint probability by just multiplying all of these different covariate probabilities of observing covariate vectors together is that we assume that each of these covariate vectors is independent of each other. So you can just use get the joint probabilities through multiplication. So then the total likelihood for the total probability that one of the m plus 1 subjects in the kth matched set is the case and the remainder are the controls is the union of the probabilities that the person with the covariate set x0k has disease and the rest are disease-free, and the probability that the person with covariate set x1k has disease and the rest are disease-free, up to the probability that person with the mth covariate set has disease and the rest are disease-free. And this is given by the probability, here's the probability that the person with covariate set x0k has disease and everyone else is disease-free. And then you add up all of the rest of those probabilities for each other subject in that strata. And you can express that more succinctly as the sum of each of those probabilities over all of those different potential individuals. then we can use the law of conditional probability from the previous lecture to calculate our conditional probability of interest, which is just a ratio of those that are calculated in those two previous slides. And this is the conditional likelihood for the kth stratum or matched set. So since we're really interested in the probability of y given the set of covariates, we can use Bayes' theorem to substitute that in. Remembering that Bayes' theorem, the statement of Bayes' theorem is probability of A given B equals probability of B given A times probability A over the probability of B. This just allows you to flip around the direction of your conditionality. So then, yeah, we can use this Bayes' theorem to substitute this whole term in for this term in the previous equation, and similarly, this term in for any of the probability given y equals 0 terms. So our likelihood now becomes what is written down here, where we plugged in this there and down there, and we plugged in this here and down here. And so there's going to be, so this likelihood, this part, the probability of y equals I and the probability of y equals 0, those are probabilities that don't depend on the strata or the particular subject, so those are going to be able to get pulled out. Similarly, we can also pull out a term which is we can also pull out from each, the numerator denominator, a product of probability of xik. And so those terms are actually going to cancel from the numerator and the denominator. And you'll end up with a form of the likelihood that looks like this. Sort of reduced, more simplified form, just in terms of the probabilities of the y's given the x's. And because we're interested in doing a regression and figuring out the relationships between the x's and the y's, we can substitute that with our Logit model to get the likelihood in terms of the intercept and the betas. And again, rearranging this to get probability, we get, by taking the inverse Logit, we get this where x beta is a vector of beta times the covariates of interest, and then alpha k is the intercept for whatever your kth stratum is. And we can substitute probability y equals 1 given this covariate pattern and probability y equals 0 given this covariate pattern for the ith subject. And here this part was just obtained by taking 1 minus probability of y equals 1 given x. And I skipped a couple algebraic steps to get here, but you can take that probability and plug it into what was on the previous slide and reduce and simplify that likelihood, and you'll end up with something that looks like this. And then you can actually take this e of k and simplify further by pulling this out of the sum. And these terms, these intercept terms, are actually going to cancel. So you have a stratum-specific likelihood here, but the intercept terms canceled, and these are said to have been conditioned out. What this means practically is that the effects of matching variables cannot be estimated. We can only estimate the covariates in the x's here, which those effects which are not the matching variables. Those are the other variables. And then you get an overall likelihood across strata, which is just the product of the likelihood for each of these strata. So the product of each of these likelihoods. So since we can't estimate the intercepts, we also cannot estimate the disease probabilities. That should be a subscript there. However, we can still include interaction terms between matching variables and exposure factors to determine whether the effect of the exposure variable is consistent across different values of the matching variable. And we would do this and interpret it the same way that we did when we used interaction terms in previous lectures. And also the log odds ratios are independent of the intercepts, so they can be estimated. Aside from this conditional likelihood behaves much like an ordinary likelihood, and you can use it to maximize, then maximize it and get estimates of your coefficients. You can also use likelihood ratio tests to compare nested models and conduct hypothesis tests for parameter estimates.